Okay, thank you, Patrick, and thank you so much for the organizers for setting this conference up to celebrate Pascal's birthday and to give me the opportunity to talk a little bit about work that I did with Pascal over a certain amount of years, and also show you some other things unrelated. Okay, so why I was, you're gonna see. Someone told me that the title of the talk looked a little bit like clickbait person. I agree it's not completely false. But anyway, so when I was somehow preparing this talk, I realized, and I'm happy that currently I'm young enough to be living this thing that is a blessing and a curse, namely mostly anything that I ever did has tracked down somewhere. So, and that was good because I could precisely track down the moment when I got contact Carl for the first time. Okay, so this is where I want to start my talk. So that was on November 5 in 2013. I was a second-year PhD student in Darmstadt, and it just happened that I had written the first research paper, co-authors, and then I thought about my future, and I thought I should get in touch with people outside of Darmstadt. So how do I do that? I thought, okay, I'm going to make a list of all the people that I think could potentially be interested in the things I did, and then I'm going to write them an email, just drawing their attention to the things I could. And that took me some courage, but eventually on this day, late at night, I somehow gathered all my courage and I wrote these emails. And one of them was to Pascal. So you see this, the original mail. It just says, blah, 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 blah. I mean, papers, and so on and so forth. And then as you do when you send an email that you're kind of scared of, I just blindly looked at the cursor and then I pressed like this and then I went to bed and like the usual thing, right? And then like a little child waiting for Père Noël to come, I was hoping that next day I would find some emails of people having answered. Okay, and so the next day I find this email. I mean, I found many of them because most people on this responded, but Pascal was the first to reply, so I start reading this email, and so it starts, Dear Egert, mixed up my family name. Boy. But then the email gets better, okay, and see. Yeah. You win as always. Okay. Okay, and so he says, congratulations for this beautiful achievement. And then there's this thing, and it's really a thing I appreciate so much in working with you and seeing how you sort of interact with your colleagues, your students. It's just this generosity and this almost infinite time that you somehow manage to sacrifice for each and every project, each of every student. So in this email, it says, if you're still interested, it could be a convenient thing to come to Orsay for 2 months. And explain all that to me, and so that's what I did. And so the year after, January 2014, I came to Orsay, and this is the first time. Okay. Well, so this is somehow the primer of the talk. Then this is also, I mean, not just for joke. The serious conference is about harmonic analysis. So what other space could I pick than BMO or harmonic analysis conference? So I'm going to work in BMO Rn. Rn is X variable, X down there. Okay, so BMO is here, and then there's an upper half space with a variable like T. And okay, and so on the space BMO, there are very many different norms that have different meanings, that are useful in various situations. So the one thing I want to look at here is the following. So you get an equivalent norm on BMO if you do the following thing to your BMO function f. F is the BMO function. Then you do an extension of this BMO function by the Poisson semigroup of the Laplacian that works X variable. And sort of this sense, there's an evolution. You can think of t direction, this kind of function in the upper half space. And then there's a certain functional called the Carlson functional, to which you can apply this extension, and then it gives you an equivalent form on BMO. And so the Carlson functional for a function capital that somehow defined here, well, you take some L2 averages on Carlson boxes like this, so this box sent to the origin. You take L2 integrals over these Carlson boxes, you divide by basically measure of just surface ball, and take the soup of D, that for all points X around the box center. The Carlson functional, you evaluate that infinity, and so that's a thing I want to. So it is, of course, think of Poisson semigroup is closely related to solving a boundary value problem for the Laplacian, but the upper half space. So this is closely related to what I want to call the BMO Dirichlet problem. Now for the Laplacian, but in n+1 dimensions, the t and the x. And this problem consists in, basically finding a harmonic function in the upper half space, the first line, for which the Carlson functional of t times the gradient thing, just like Poisson semigroup slide, is in L infinity. And in some sense, this extension, when you go down to the boundary, should obtain the boundary. Now, the possible questions, like most PDEs ask, like, is there a solution? Is there a unique solution? And in which sense can I sort of explain the behavior? Valid questions that. Okay, so one thing that you show is take the Poisson extension, how it's made. This is going to create a harmonic function. Convergence at the boundary can be a delicate thing depending on which sort of convergence you want. There are two types of results, all this stuff. I don't want to do too much. Okay, what do I want to do then? So this is classic theory. I skip, okay? I go somewhere else. I go to California before I start doing math. So there's a picture, Kleinzellers in Sonoma Valley. And there was a harmonic analysis program at MSRI, and at some point, Pascal, myself, and former student of E, Eduardo, we went to do wine tasting in the California. And there was, in particular, this Kleinzellers is somehow the one that stayed in my memory because we were sitting there and you can taste like for wine. But then because we were talking in French, these Americans thought that they had to impress on us because we are the connoisseur of wine. And so we were tasting much more wine than we bought. Okay, so and so we realized that quite a good idea. So we kept trying implementing this thing at other wineries, and anyway, okay. There was a don't ask how we got from one place to the other. There was this particular wine that very delicious. Pascal opened the bottle only in 23, kept it for a longer time. Mine was anyway. Okay, so why am I telling this is because at the time when we were visiting these vineyards, this was in Berkeley, and we were working on a thing, namely we wanted to try to prove uniqueness in elliptic boundary value problems in situations where you do not have pointwise values. So there is no the George-Moser property, and think of PDEs complex coefficients, then uniqueness can really be an issue. And so we were thinking about this in the context of LP Dirichlet problem for elliptic system. But then somehow, I think Fema was there, and we were talking at some point about BMO. So the question arises, what happens to BMO theory I showed you for Laplace? I replace this minus Laplace X variable, I replace by a more general elliptic. Okay, and the operator we're thinking about was convergence form operator. D are like the coefficients bounded, and we could have like a multiplicative perturbation by function A, A function, real part bounded from below by. In this case, operator L gets sectorial of some angle, possibly larger than pi over 2. Not a semi-group generator, but there's still a possibility. So it's a legitimate question. What happens to the BMO theory I work with these, particularly these coefficients A and D, so they fit setting with. All right, and so at least when I take an L2 function, then I could have a look at the Poisson extension defined by the functional calculus 2, because it's a nice operator in L2. And when you do some formal calculations, you take this guy and you take two derivatives t. See if I derive twice in t, then I'll get a square root down. I get another square root down. So I'm going to solve this problem dt squared u plus L of 0. Formally, sense of semigroup, when t is equal to 0, I recover f. So I solve this problem in an upper half space. And then if you write down just what the operator L is, you recover, and from the first line plugging L becomes an elliptic PDE, and we call it with block structure and P dependent. So what does that mean? Well, it means because this operator L is the same operator and it's just acting basically in the boundary. So A and D, they only X. If I look at the PDE, that's P and X, so independent, the vertex, right? Usual starting point, boundary value problems type. And I call it block structure. We call it block structure because there are two blocks. There's a second order term called only t derivative. There's a second order elliptic thing involved only x derivatives, but x t derivatives, they don't get. If you would write it in terms of the gradient t and x convergence, then there would be a coefficient metric 2 by 2, and that's a block structure because there's no mix. Okay, so formally for this problem, you can construct a solution with L2. Okay, then Pascal, at some point, I think I could track it down, May in 17, he made an observation. And so he looked at this Dirichlet problem, except that now the operator for which I want to solve is not the Laplacian, but is elliptic guy with block structure. And I still have the Carlson, the gradient group. And as we were talking about uniqueness, we wanted to see if the proofs that we had for LP data they could be extended to BMO. Okay, so Pascal realized that this works if you take a certain convergence towards the boundary data as t goes to 0. Cesaro means to converge in L2 log slicewise. So you fix like a compact set in x variable. Just restrict all your attention to this compact set. You look what happens on these t slices. Cesaro means they converge to f. And then to prove that there is at most one solution, so there's uniqueness in this problem under the assumption that the Poisson semigroup associated with L, the Gaiac boundary, should be uniformly bounded semigroup LP for P larger than the dimension. That was the condition. Okay, and so he's what he said. So I think he said, I can prove the missing estimate. So you can imagine there were like longer calculations. It was discussion with Chema. Chema was grateful. He wanted to look Monday. Not sure if that happened. He can tell us at some point. And so what I want to show you is like what was the missing estimate and why does this assumption sort of play such a crucial role? Because if you think about it and you see it for the first time, it might appear strange to you because it's a BMO problem. So BMO is the endpoint. Something, if you think of LP spaces, it's certainly closer to L infinity than to LP for some P larger than. So the question is how is this assumption, which has nothing to do with L infinity type estimate, becoming important in proving unique? Okay. So let's have a look how and why. Okay, so if you've seen these proofs of uniqueness, you are going, but you don't have, if you have seen proofs like this before, you're going to realize that this is a very common strategy. The additional challenge only that solutions have no pointwise estimate, and objects like layer potential, fundamental solutions, they are not given by integral. Okay, so the challenge in writing this thing out was somehow to emulate the argument find everywhere, but you must not use kernels or pointwise bound. Everything has to happen on the level of operator. Operators that are just operators. Okay, so let's suppose then, because it's a linear problem, for uniqueness, I just suppose that I solve the problem boundary data 0, and I have to come to the conclusion that the solution. Okay, suppose that U is a solution with data, and then I want to prove that U is equal to 0 by testing U against a bunch of tests. And for technical reasons, you're going to see in a second why I will not test it against every compactly supported function. The upper half space smooth, that would certainly be sufficient, but using the fact that the solution solves the problem, solving the problem, not just solving the PDE, but it also means satisfying the interior control on this Carlson. Okay, and so this you can think of somehow limiting the growth or how extreme this function is, somehow tamed by the Carlson functional. And when you take that into account, it would be enough to prove actually that testing U against test functions that are time derivative, p derivative, and divergences of other test functions. That calculation first to figure out that the function is independent of some variables, and then there's growth. Okay, so let's take that for granted. And then we are going, in some sense, we're going to do some harm to this function g. And the things that we're doing to this function, they might destroy support information. So beforehand, sort of introduce theta is a Lipschitz function that is equal to 1 on the support. We're going to throw that in the argument to somehow keep track of the support assumption g that we had. Okay, so theta is just 1 on the support of g. And then I take an adjoint solution. Very classic argument. I solve a joint problem in the full space, say, L star of H is going to be G, and G is test. When I do that, you do a computation. Well, you start with the testing pair that becomes 0 eventually. Then the G you replace by L star of H, the right-hand side of the joint equation. The theta you introduce beforehand so that the theta will keep track of the support all the way. Use the definition of the adjoint operator, throw things to the other side. So A, capital A is the coefficient thing called small a and d. Okay, so that becomes by this thing. Then you do calculations with the product, calculate by the product gradient, get terms. At some point, you want to use that used solution. So do another product rule. The theta goes to the other side. Product reverse, order to create this term with a gradient of U paired with gradient theta H. And then because U is a solution to the equation, say that this term gets this one calculation do. Now we do another calculation of the same type with a very special function. Okay, so what we're going to do is we're going to take this guy H, going to evaluate it at the boundary, and then at the boundary we restart the flow by the adjoint quasi-semigroup. We're going to call this H. The idea somehow is that we have to do good things at the boundary. So we want to compare this H that we do not know so much about to a semigroup evolution, which we have much better track going. Okay, so we have this H and the H1. They're both adjoint solutions to things and the boundary. Okay, and then you redo the same calculation, except that I start from here and I replace H by H1, because H1 joint solution, right hand side 0. This term is going to vanish. So when I plug it together, I keep u of t, here I keep H minus H1, 1, both. That's all that. So that's what you have. Very classical. Okay, I just copied for convenience so that I don't have to skip back and forth. Just copied over here the point until which we manage to, to run the argument. Okay. And so what's the goal of this? I mean, the left-hand side, the testing should become 0. So the idea is I want to let the theta somehow tend to 1 in a way that is adapted to my problem. Because if formally theta would equal to 1, you see there's a gradient of theta everywhere, and the right-hand side. Okay, so my goal is to let theta tend to 1 in a fashion that allows me to prove that the terms on the right-hand side tend to 0. If I manage to do this, u paired against g is 0. Okay. So what sort of theta use? Well, Pascal realized who made this drawing. I mean, somehow this is your favorite function. I don't know. I mean, if you've been working with Pascal, you probably know what I'm talking about. Yeah, you can. Sure. I think I must have like 20 mails of you that sort of do the sketch of this. Okay, there's a bump function, a piecewise linear thing. Okay, so what you do is the theta, you basically truncate in a linear way at the boundary, at infinity, and in space. You also do something. So it's going to be 1 on some large part, and then there's a control way goes 0. So that. Okay, and then you look at these error terms, you would write them out. I'm not going to do that for you because it's too technical to show that. But you can imagine how these terms in principle would look like. Then there's, you take the gradient of theta, because theta is 1 on a very large portion of upper half space. Gradient of theta is going to be 0 on a large portion. You just recover boundaries. For example, you will recover something where you did the truncation in space, the x variable. You're going to recover an integral in the x variable where you're integrating on an annulus that's really far away. Okay, so you get multiple pieces of this type. You have to handle all of them separately. There's different methods for every piece. And a main contribution that you pick up is the one that you have applied. So it's an integral. You go on something like a Carlson box 0 to 2m, but space you just have annulus. You have a 1 over m that comes somehow from the gradient L infinity norm of the cutoff, and then there's u against the gradient x. This thing should. Okay. And so what Pascal attached to this email I showed you proved is he had a way of controlling this guy at the cost of somehow a logarithm. It's not completely unexpected when you work in BMO stuff things. At the cost of a logarithm, he could somehow pretend that this u was more or less constant. Came from the Carlson control, we bound on the gradient, concrete arguments. the constant implicit here is going to depend on you. Don't care. Only the m that we want to follow. Everything we're doing is completely qualitative. There's no need to prove serious estimates. It just has to go. Okay, and then what you get is there's a soup, and then there's some integrals like Whitney type, t of 2t space, and then there's okay. This is how far we get, and nothing concerning assumptions of Poisson semiconductors. Also did not do anything spectacular here, except that we had a beautiful estimate that sort of eliminates the. Okay, so we are at this point, and now comes the thing that is kind of interesting and that distinguishes this way of proving uniqueness from things where you use pointwise bounds on kernel-like. Okay, and so there is this abstract single layer potential that Andreas Rose. And what you have is that basically the time, the t derivative of the single layer for the adjoint equation, it is something like the Poisson semi-adjoint. And in these questions of uniqueness, what we use all the time is that we can explicitly construct the inverse of this. I mean, L star is just the elliptic operator, find variation, just the Lex-Milgram theorem shows that this guy is invertible homogeneous double F space. You can explicitly compute the inverse on nice functions using this Poisson semi. Okay? So what we knew is that A, the guy that we introduced at the beginning of the calculus, L star inverse of G, that was somehow given by convolution of the right-hand side with a single layer, and because this G was a time derivative, you know, we're doing convolution with a time derivative, which is a completely non-singular object because Poisson semi, there's uniform bound, there's no singularity. So you have a nice formula that says A is basically convolution integral involving the Poisson semi. It's only convolution in T. There's no need to believe that X this has anything to do with. And you know, by construction H1, you got it by taking this expression. You first set T is equal to 0, and you get some integral involved Poisson semigroup. And then on the exterior, you reapply Poisson semigroup. There's going to be a similar formula. These are just integrals over Poisson semigroup. And now these G guys, they were compactly supported. So actually, I'm not even integrating over the whole reals, but I'm only integrating about compact. Okay, so it's totally believable, I think. This integral just goes on a compact set. And I'm not caring at all about good estimates. I just something that I could just brutally put LP norms inside of the integral. I throw LP norms on this, and I use operator norm bounds. This. Okay, so what I get is that I control the difference of two guys, say LP prime, provided that the Poisson semigroup for L is uniformly bounded. Why is there a change in P and P prime? Well, the assumption was on the Poisson semigroup joint. And this is the estimate that completely qualitative, but this thing stays bound. So then, when you put it together, we have gathered two information. We want to kill that guy when m goes to infinity, and we have this information from the abstract semigroup. And then we do something that looks, I mean, extremely stupid because it seems to waste a lot of things, but it's enough to complete the argument. What you just do is, well, this is a L1 norm, some ball. Here there's a soup with an average, so you can just control that by just a soup of slice-wise L1 norm. Then it's the L1 norm on a ball. You use Hölder's inequality to switch to LP prime norm. And when you do that, you get LP norm of the one function integrated over the ball. So this gives a contribution which is like the measure of this ball, m to the n, over p. Now, this was a guy bounded. And then you gather your exponents. You see if I manage to say that this exponent that goes with the m, the positive one, this is less than 1, then the 1 over m with a logarithm, they will be able to pull that guy to 0. Now, when does this power become less than 1 is precisely on large. If I assume out of nothing that the Poisson semigroup would be bounded on LP, p larger than n, then the argument. Okay? Then I let m go to infinity, thing goes to 0, and I'm. Okay, so the wrap up is, if I want to study LP, the BMO Dirichlet problem for this elliptic operator, a uniform LP bound for the Poisson semigroup for p larger than n, that's enough to prove unique. Now, what is interesting about the thing is that the theorem about BMO extensions to the upper half space, but at no point did I say anything about the semigroup being defined, let alone bounded on BMO. Okay? And in general, this is, there's general fact about LP bounded Poisson semigroup for the operators. The thing is that when p is equal to 2, boundedness is always true. Then you can move away from p equal to somehow the Sobolev conjugate upper and lower of 2. There's a neighborhood in the LP scale where you have bound. Neighborhood slightly larger than the Sobolev. But for any point outside of the region just determined by this path, there's a counter. LP bounded fail out. And so you see, well, 2 dimensions, n is equal to 2 because this guy is never larger than 1/2. 2 dimensions, this thing is always, so then you get BMO or by duality H1 bounded. But as soon as dimension is at least 3, you cannot expect the bounded Poisson. This count. But when you just want this condition to be satisfied some p larger than n, start doing the calculations again. You see at least 3 dimensions, and in 4 dimensions, it's always for free, and it just can start failing when you're in dimension 5. So there's this gap. Well, what's next? Okay, we did other things. We let it rest for some time, and we just slowly and surely picked up this elliptic boundary value problem, 2019, and then thanks to the pandemic. Okay, so at some point, at least I felt kind of unmotivated to continue working on this project. You probably felt it. Sometimes I didn't want to, but then, as always, you sort of managed to motivate me and put all my effort in this work because, someday in 2020, Pascal sent me an email. There was a fiche for announcement for a prize, book prize for a monograph, and he said, well, would that be something for our book? And I said, yeah, why not? Let's try. It's a good idea. Okay, and so from this moment on until November of the same year, it was full speed ahead of reworking all these uniqueness, these questions, so on and so forth. And so back to topic, a little bit earlier, somehow I posed the question that you would probably already have posed because I proved unique. There's a unique solution to this problem, but does there exist a solution? And I even construct a solution. Okay, so here now there's French texting, usual mistakes I make with the language, try to track them. In English, it says, May 8th for my wife's birthday. Continued. Regarding the Dirichlet problem, can we construct a solution? And then I said, I think one should use weak star density to somehow extend the Poisson semigroup to BMO, but there's no information available on the Poisson semigroup on the dual Hardy space. Of course, because if I would have boundedness on the semigroup on the Hardy space, I could do interpolation with the L2 theory and some duality arguments, and I would get LP boundedness for every point, which I already know is false. It's not the assumption that we used for unique. Okay, so Pascal says, oh, I don't know, I'll think about it. Okay, so let's see how we thought about it and what. So from now on, I'm going to put myself in the setting that for whatever reason, this Poisson semigroup bounded on LP for some p larger than dimension. So this is the setting where we know there's this one solution, but now I'm greedy and I want to have it. And so F is in BMO, and I need to give a meaning to this Poisson semigroup acting on this BMO. But it's BMO, so the semigroup is only defined on L2. So there's no density from L2 can help me, and no duality can help me because the semigroup is also not properly acting in the Hardy. So what should I do? And the thing that I should do is to invoke off-diagonal. Okay, so if you've never seen that before, don't worry, I'll guide you through. It's just one instance where we're going to use this estimate. So what this off-diagonal estimate says is I take some function f, localized f, I let it evolve through the Poisson semigroup, and then I evaluate what I get, e, and if that e and f, they are separated in space, then I pick up some. Usually when you want to do these tangents of operator via off-diagonal decay, you need a lot of decay. But for the Poisson semigroup, just do the calculation with a Laplacian, you have explicit kernel, there's not going to be much. There's only off-diagonal decay of order 1. Okay, so t you can ignore because I first want to give meaning to that for every t, so t for me is just constant. And so there's only power minus 1. There's no way to get any better. You shouldn't stop yet because, well, if I work in L2 and I just have order 1, then the story is over. But I have this assumption on the Poisson semigroup LP, so I also get order 1 off-diagonal estimate, but with respect to LP norm. Okay, and very poor decay, but with respect to LP norms with very large p, that can behave in a way similarly to having much decay. Okay, and so I claim that these off-diagonal estimates, they're enough to define the Poisson semigroup acting on L infinity function. The way you do it is, well, you take just any ball, you define the action of the Poisson semigroup by letting it act on these truncated functions. These are bounded functions, compact support, so they are in L2. The Poisson semigroup is defined, and I try to do the limit as j goes to infinity. And I'm going to show you in a second that this limit exists. For that, I'm going to write it as a series. Now, just this ball, I write as a decomposition annually, and I sum them up. What I've done here. Now, I want to show that the series converges. Okay, so the series up here, same thing, nothing happens. And then I claim that this converges locally in LP because if I take LP norm of each of these summons in some set E, if the J is very large, then the distance of the annulus to this set E is about 2 to the J. So the off-diagonal decay, just ignore the T, let me pick up 2 to the J to the minus 1 times the function localized by the LP norm. And now I stupidly estimate the LP norm on a bounded set by the L infinity norm. I pick up the measure to the power n over p. So the measure picks up a 2 to the j, but if p is large, then this is a small number. And you see, I'm allowed to pick up anything that is less than 1. So once again, if p is larger than n, then this growth is less than the decay I get from the very poor off-diagonal estimate. So this is enough. Now you can check that this definition is the choice of the ball, and it's a nice extension because this extension has a conservation property. You apply it to constant function, you get back. And this fact I'm going to use, and I'm going to claim that in the same way I cannot even extend the to L infinity, but I can go further, I can extend it to BMO. The extension I do exactly the same way. You see, I just take the F, then I do minus the average plus the average. Poisson semigroup acting on the average just gives back the average. For F minus the average, I'm going to do the same decomposition to annulus regions. I'm going to use the off-diagonal decay on each of these well-localized pieces. I pick up the same stuff, except that now when I want to relate it to the BMO norm, I cannot just pull out the L infinity norm, but I have to do some bootstrapping argument because I'm on a large ball and I subtract the average on a small ball. Not going to be uniformly bounded, but the additional growth that I'm picking up by the bootstrapping is logarithmic in the scale. So here it's 2 to the j, so I pick up a linear factor j. And that's okay. B is larger than n. The linear factor not going to be any harm against the x. Once against the series converges, I have extended the semigroup O. And so the theorem that grew out of that is, well, if f is a BMO function, and I use this new definition of the Poisson semigroup on BMO, then this thing turns out to be a solution, and thus the unique solution to the BMO Dirichlet. And you have the nice things that you would expect. You have control of the interior control that problem by the data, and you have non-tangential convergence. Beautiful. Seems like the end of the story for me. Yeah, you know what's coming next, right? This? Of course. Of course. Okay, so the question is, Pascal raised the question, very valid question, of course, what is about the lower bound for the calculus? We could do that, then it would somehow justify that the construction we are about to do is even more natural, because it would give an equivalent norm on BMO through the Poisson extensions of BMO functions via these semigroups. Okay, and then there's a technique. See in these kinds of estimates, there are duality techniques. Yeah, try to use a very nice operator in the same class, like Laplacian. In this case, slightly perturbed Laplacian. For this guy, we knew from all the work doing that the Hardy Dirichlet problem well posed, and then try for duality. Okay, so the short answer is yes, duality argument using the H1 Dirichlet problem for the adjoint equation allows you to prove the lower bound for your unique solution BMO problem. Honest answer is yes, still yes. Good. But this definition of the semigroup really makes your life quite hard, because the semigroup, we just write it as a semigroup, but it's defined as this infinite sum, and this is an infinite sum that has to do strange things because it is not propagating the space to which you apply the semigroup in the first place. Even though we write it as a semigroup, definitely not a semigroup. You apply it to a BMO function, you go an epsilon up, there's no reason to believe you're still slicewise. Okay, so arguments with semigroup, formally, the proof just goes through. But if you remember the definition that you gave to this object, definitely not the case. So, you know, there's to need the smooth decomposition instead of just a ball cut thing. And this was Pascal's idea, May 19. He says, well, to replace the characteristic functions by smooth functions. And then the scary thing in this message he sent me is that there's going to be error terms, and it's unbelievably complex. That's what it was. And I said, yeah, I tried to do that yesterday, and unfortunately, there's an error term. And anyway, I'm going to spare you this story. in the end, okay? So in the end, it works. And so the Poisson extension of this BMO function under the background assumption Poisson semigroup that I'm having all the time gives you a unique solution to the BMO Dirichlet problem, and you get an equivalent norm, just like for the ordinary Laplacian, through t times the gradient. And I call this unexpected because we don't know anything about the BMO norm, any of these semigroup operators, except when it's not semigroup is always a slicewise. If t, you do something like that. Here, things happen simultaneously in time and space. What you keep is the fact that you solve the p, but what you lose is the fact that there's a. Okay, so all this is under the assumption that the Poisson bounded if t larger than n. This is always true when dimension 3 or 4. And in higher dimensions, it depends on what you can prove for your Poisson. We do not know today any reasonable statement of the type that says if the BMO Dirichlet problem for such an operator, whether or not it satisfies background assumption, suppose the problem is well posed, does this somehow backfire on the LP theory of the Poisson semigroup and you can infer anything reasonable? Not. We do know is that the things I showed you, they are somehow part of a bigger picture. Namely, you can also treat LP Dirichlet problem. The thing is that if your Poisson semigroup happens to be bounded LP for large 2, this is always true for every such operator, then the range of exponent Q for which you can solve an LQ Dirichlet problem with non-trivial convergence boundary and so forth, this problem is well posed, and the range of exponents definitely exceeds the range of exponents which are bounded, because LP bounded semigroup gives you LQ Dirichlet problem well posed, you upper sub in one exponent. This is in complete coherence with the things I showed here, because P is larger than N. Taking a Sobolev conjugate brings you beyond infinity. Beyond infinity, you just think of the exponents as the space towards which the Sobolev embedding is up. Right. And so the project we did turned out to book. Today's result, they're mainly the 18. I told you you should not read other chapters before. But the book is out there. This is how it looked like. And yeah, so I think in retrospective, one of the projects that stick the hardest in my mind, and I have like many different memories of what happened during the write-up of this book. In particular, we received this prize in the end that Cal was suggesting we should try for. So this ceremony, it was great fun most of the time. There's old movies, there's some outtake. Okay, so the outtake is see our desperation before the deadline to send in the book. So I was working hard at night, November, midnight. I was saying, I'm not sure, something, blah, blah, blah. This is like, I was in despair. And then I went to sleep, and the next morning I woke up and I saw that I was working even later. And she just said, am I stupid? And then without saying anything else, just continued work. This was, okay, anyway. So thank you for listening, and merci Pascal pour nos projets au cours des dernières 10 années.
Thank you, Moritz, for this beautiful talk. Are there questions? I can move, so give you up.
Yeah, so first, okay. Yeah, first of all, thanks for your talk. You explained to us this condition that P is strictly larger than n by some applications of Hölder and so on. And in the end, you explained that somehow, to show well posts of the Dirichlet problem, you somehow need one Sobolev exponent less than to have existence of the semigroup. Is it somehow that you gain this one Sobolev conjugate? Is it? Can you understand it on a bit less technical level than on these Hölder applications? So is there like a heuristic explication why you gain this, or is it just from the calculations?
That's a good question. It comes mainly from the calculation, because if you try to bound these things, you use the semigroup theory, and at some point in the calculations, we realize that we do not need the full strength of group theory. Get away with not using that semigroup bounded, but something less. There are many estimates, not always this Hölder thing. There are many estimates where you are definitely done when the semigroup is bounded, but then you get estimates in which you can still wiggle around the component. Somehow, no matter what you do, the wiggling always amounts to having one addition. I mean, there's a dual thing that was known before, and that we look at the regularity problem. Go one Sobolev conjugate down, identification hard basis operators go one Sobolev conjugate below the semigroup. Somehow inspired by this, I mean, we started trying to see that for the Dirichlet problem, there's the opposite. But yeah, the thing is, I mean, I said there's no reasonable statement to go back. This is partly related to the thing that, yeah, we don't know how to get our hands. Let's no more.
Merci Moritz. In English. You reminded me things that I had forgotten. That's moving. I want to thank you for. So I reminded from your lecture that in these 4 years where I was busy with other things, people know, some don't. But you kept me mathematically alive, and more than mathematics. Thank you.
Other questions? Yes.
So you spoke about the Dirichlet problem, and do you have something concerning heat equation? I mean, you could consider heat semigroup and ask similar uniqueness questions. I don't know.
Okay, I mean, yeah, that's okay. So the question is about the heat semigroup. By the way, I mean, if you speak to the microphone, it will be on the recording. It's just I said my voice was too loud. I don't want to have like a tour from. Okay, so the question about heat equation. I mean, you can ask questions like for which L space heat equation the heat semigroup bound. Fine. So probably that's a question for Pascal and Ben, right?
Back to Pascal. Thank you, Baptiste, for the question. So my answer is you talk to this guy just next behind you, and you wait for his thesis to come. There are already some works on it on the archive about uniqueness under some conditions, but it's close to the end. We're finishing something with this guy.
So this is the results for the PDE side. If you're interested just in operator theoretic back assumption that we had that group bounded P, should not use a multiplicative perturbation, but then if this operator generates the heat semigroup, ask when it's bounded P, and then there's multiple conditions that, except for maybe endpoint results are equivalent, the interval of exponents t for which Poisson is bounded, for which heat is bounded, for which operator satisfies uniform resolved estimate. They're all intervals. They share the same interval. So this is why for heat equation also you expect to work similar range.
Another one more thing about parabolic situation. You use an actual heat semigroup, as Moritz said, but then the problem about boundedness disappears because you have a lot of decay of the heat semigroup compared to the Poisson semigroup. So in some sense, it's easier.
Any other question? If not, let's thank the speaker again. And